Good morning, everyone. So this is a slightly unusual project in as much as it emerged as a collaboration between 4 climate science bloggers and 2 scientists at the National Climate Data Center, Menne and Claude Williams. And we wanted to address the often vexing problem of how much urbanization has influenced climate trends in the United States over the last century, and how well existing homogenization procedures remove these urban influences, and if any additional urban adjustments to the temperature record might be warranted by any residual urbanization signal. And to step back a little bit and discuss the effect of urbanization on temperature, it's very obvious that urban areas tend to be warmer, all things being equal, than non-urban areas. But the impact of that urban warmth on the temperature trends is a little bit more difficult, simply because the trends are a change over time, and if the instrument is initially built in an urban area, it's not necessarily clear how that urban area changing its composition over time will affect the temperatures, versus a station that started out in a rural area and had an urban area grow around it. And there's large variations in estimates of the impact of urbanization on trends in the literature. You see some very small ones, for example, the Parker paper a few years back, and larger ones, say the Jones study in China. And there's also the issue, especially in the US, where, well, and in the world in general, where the measurement stations tend to be disproportionately located in urbanized areas. That's not to say that the majority of stations are urban, but rather there are more urban stations than the proportion of the land area that's covered by urban centers. Which means while the urban heating is a real heating and should be measured as part of the global energy budget, it's not necessarily something we want spread out to the extent it currently is. There's also a very big open question of the importance of microscale versus mesoscale effects, so how much the station siting matters versus how much the surrounding area matters. So if the station is on a concrete parking lot, even if it's in a very rural area, there might be a strong localized heating. And that's something that we need to address better, and it's something that a number of folks are working on addressing right now. Finally, there's the expectation that UHI will impact minimum temperatures more than maximum temperatures. That's something that we've seen a little bit in the context of this study as well. So for the study itself, we took the US Historical Climatological Network and tried to see how much heating, or how much difference there is between the urban stations of the network and the rural stations of the network. And the US HCN was set up in the early 80s. It was primarily a selection of co-op stations with long records that were chosen, that were well geographically distributed to represent the long-term climate of the country. And we have the benefit with US HCN of having a very highly sampled network. So compared to the rest of the world, for example, in GHCN, US HCN has a lot of stations, about 1,200 covering the US, and that lets us dice them up into different bits without necessarily losing a lot of the spatial coverage needed to construct a spatial temperature. And US HCN data is homogenized through 2 steps. First, there's time of observation adjustments, which we don't really examine in this project simply because A, they're less controversial, and B, they tend to be correlated with urban form, and they'll mess up the analysis. But perhaps more importantly is the homogenization, the pairwise homogenization algorithm that Menne and Williams developed. And for that, they compare individual HCN stations to the surrounding co-op stations, both to automatically detect inhomogeneities and to correct them. Prior to HCN version 2, there actually was an explicit urbanization correction in the HCN temperature. But version 2, which switched to this automated inhomogeneity detection system, does not include an explicit correction. The idea is that the automated inhomogeneity detection will sort of remove the urban signal by itself. So as part of this paper, we wanted to test that. We wanted to see both in the time of observation adjusted data and in the homogenized data the extent to which there was any residual urban signal by comparing the rural and urban stations. But it's sort of an open question of what is an urban station, and it's often hard to define. And so we chose 4 different proxies for urbanity to use in determining which stations were urban and which stations were rural. The first of those were urban boundaries through a product called GRUMP that's produced by Columbia University. Second was satellite nightlights, which is also used by Gistemp, Hansen et al. Third was impermeable surfaces, primarily work by Eldridge and Imhoff, using a lot of USGS data. And finally was population growth data, so sort of census data slightly modeled at a 1 kilometer level to look at the population growth for each kilometer in the U.S. from 1930 to today. All of these, I should mention, all of these urbanity proxies are examined at a 1 square kilometer level, and stations are assigned an urban or rural categorization based on their latitude and longitude, and based on a cutoff that's determined when possible by the literature. So urban boundaries are pretty easy. It's either urban or rural. Satellite night lights, we try to use a value that Hansen uses in the GISTEMP analysis. Impermeable surfaces, we use 10%, which Imhoff recommends. And population growth, it's a little bit more subjective, but we just use 10 people or more population growth per square kilometer to divide rural and urban. And the way it ends up breaking down is the night lights and impermeable surfaces sets have a small number of urban stations, a large number of rural stations. The urban boundaries and population growth sets are more even. About half the stations are categorized as urban and half as rural. And we use 2 different methods to analyze the results of the urban and rural stations. The first is a station pairing method. So we take all possible permutations of urban and rural station pairs that meet a set of criteria, so they're within 100 miles of each other, and they have the same sensor type. And in the case of MMTS stations, they have a transition date within 5 years of the other. And we do that to try to remove the bias due to sensor type changes. Particularly, there's a max cooling bias introduced by the MMTS transition. And then we perform a weighted regression of urban pair anomaly differences, and we weight it by unique urban station. That's to reduce sort of spatial clustering. The second is the spatial gridding method. It's sort of the standard method of assigning each station to a latitude and longitude grid, create average rural and urban anomalies separately by grid cells, and create a CONUS weighted average for each difference of them, and use a regression method to correct for autocorrelation in the data. We also wanted to test the potential urban blending in the homogenization procedure. So because stations that have inhomogeneities in the US HCN network are corrected by nearby co-op stations, it's possible that a rural HCN station with an inhomogeneity could be corrected by an urban co-op station. It could sort of blend in some urban signal. So to test that, we ran the pairwise homogenization algorithm that Menne and Williams developed using only rural co-op stations. And we saw that using only rural co-op stations, rural stations had a slightly lower trend than using all co-op stations. Interestingly, using only urban co-op stations, there's a much higher trend, which at least shows that, in theory, it's possible to have some blending in, though it seems in practice that it isn't particularly large. But just in case, we also included this series as a third one we were testing. So. Here are the results we got for the time of observation data. The solid line is the station pair method. The lighter line is the spatial gridding method. And this was actually somewhat of a surprise to us, just how large the signal was in the time of observation data. In some cases, over the course of the century, there was as much as a 0.5 C difference in urban and rural temperatures. For others, it was a little bit smaller. And there's the 4 graphs of the 4 different urbanity proxies, so GRUMP, night lights, ISA, and population growth. But once we apply the homogenization algorithm, it becomes much smaller. There are still some differences, especially prior to 1950, but the majority of the signal was removed after homogenization. And finally, when we look at only the rural homogenization, so only using rural co-op stations to run the homogenization algorithm, we see something fairly similar. I'll go back and forth between those really quick. But especially in the early part of the century, there's a much stronger UHI signal, or urban-rural difference, in the rural co-op homogenized series. This might, to some extent, be simply because there's less rural stations back then, so there's less inhomogeneities that are corrected, and we're continuing to look into this to figure out the best way to refine it. So a little bit of trend results. This is over the full century, and sorry, the graph's a little bit complicated, but the circles are the time of observation data, the diamonds are the standard homogenized data, and the triangles are the rural co-op only homogenized data. The solid shapes are the station pairing method, and the empty shapes are the spatial gridding method. So you can see here that there's the largest signal in the time of observation data, but there is some remaining signal over the full century in the homogenized data, especially it's a little bit larger in the minimum than the maximum that's present in both. Here's if we look at the difference between rural stations and all stations, and I apologize, the confidence intervals in this graph are abnormally small because there's collinearity between rural and all stations that needs to be corrected, but the means are accurate here. And what we see here is that over the full century, the rural stations warm about 15% less than all stations in the time of observation data, and about 5 to 12% less than all stations in the homogenized data. For the min, and the max is somewhat similar. However, if we look only at the last 50 years, the picture is a little bit different. Here we see fairly large differences in the time of observation adjusted data, but differences that are not statistically significant from zero in the homogenized data, both for the all co-op homogenized data and the rural-only co-op homogenized data. And that's also mostly true for the maximum as well as minimum temperatures. Similarly, if we look at the difference in trends between the rural stations and all stations, and again, confidence intervals here are abnormally small, we again see that in most cases they're not statistically significantly different from zero over the last half century. And that was quite interesting to us, that there seems to be a signal that's not being properly removed at the beginning of the century, but seems to be mostly removed near the end of the century. So to conclude quickly, urban and rural differences are significant over the full century, particularly in the time of observation adjusted min data, but they're mitigated by existing homogenization procedures, and in most cases are not significant over the past 50 years post-homogenization. It's sort of an open question for us how reliable our urbanity proxies are going back 100 years. Obviously, except for the population growth proxy, we're taking a current snapshot of urban form, and a current snapshot of urban form isn't necessarily what urban form looked like in 1930. That said, we would expect places to rarely de-urbanize. The majority of the urban signal will be captured in the stations we're currently categorizing as urban. Obviously, there'll be a few outliers, places like Detroit. But in general, we expect most of the urban signal to be contained there. So we also found that urban correlated factors may account for up to 15% of CONUS warming over the past century in the unhomogenized data, and 5 to 10% in the homogenized data. However, over the last 50 years, they only account for about 5% of CONUS warming in the TOB data, and in most cases are not significantly different from zero in the homogenized data. That said, the mean is in all cases slightly above, or almost all cases slightly above zero, so there might be a little bit of signal left there. So it may be worth considering, and this is something we want to look into further, the inclusion of additional urban warming correction in the US HCN. And this is something that NASA does in their temperature record. So in NASA's GISTemp, they take NCDC data, the homogenized data, and they apply an additional night-late-based urban correction to it, whereas NCDC doesn't currently. So we want to figure out if such a correction should be added and what effect it will have. So the next steps on this project, we are currently running the homogenized data, both the rural homogenized and the all homogenized data, through NASA's GISTemp night-light correction, and we want to look at the urban-rural differences for each of our urbanity proxies after it's had an additional night-light correction to see if there's any residual UHI signal left. So, and I'd be happy to answer any questions folks have. I definitely agree with you there that the warming occurring in those urban stations is real warming. And this is mainly geared toward reconstructing regional and global temperatures. And for local temperatures, obviously, you would want to use the best estimate of the local signal. And again, there's the challenge in removing real inhomogeneities in local stations, things like station moves or instrument changes, while maintaining a real urban signal. And that's not something, and Matt might be able to correct me here, that the pairwise homogenization algorithm does particularly well right now. But
that's a good assessment, and we've tried to do that, and there's other kinds of local signals in there that probably have nothing to do with a mesoscale forming, and there's no clean way to separate microscale mirrored local trends from mesoscale warming without resorting to some other information to bring in. So it's possible that it's going to take some work to get there. So leave the urban signal in there, try to figure out where it really is.
I think in the 1930s, a lot of the urban, there were a lot of stations that were in cities that were moved to rural areas.
Mm-hmm.
Would you take station location moves into account?
So we haven't explicitly, but to the extent that they're documented, the homogenization algorithm uses them as to inform its detection of inhomogeneities. But that is, especially around that time, an important signal that's happening, the move either to airports or to more rural areas from cities, and that could account for some of the differences then, and it couldn't be completely corrected for in the, especially because the homogenization procedure is relatively incomplete back then, because there's less co-op stations to work with to correct for inhomogeneities. So that could certainly be one of the drivers of the early century things we're seeing. Thank you, everyone.
Thank you.